Okay, before we do any more examples of triple integrals, I want to just take a moment and try to answer this question. What does it mean? Why are we doing these triple integrals? What are some applications where we would actually be doing this? Because of course, geometrically, what we're doing is we're finding a signed hypervolume in 4 space. That doesn't feel very practical. So let's suppose that I had rho of x, y, z equals a density function. So that would be giving me mass now per unit volume. So in 2 space we had mass per unit area when we were working with a lamina. Now we're working with 3-dimensional solids, so we would have mass per unit volume. If I take a look at the triple integral over E of the density dV, that's just going to be the mass of E. Very often, if I want to figure out what an integral means, I can say, well, what does the integrand mean? This is mass per volume. dV means volume. What do I get if I multiply mass per volume times volume? Oh, I get mass. And that's because integration is basically replacing multiplication. If the density was constant, to find the mass, I would simply multiply the density times the volume. Since it's not constant, we go into this process of chopping and approximating. When we're approximating things, we're basically saying, okay, let's suppose that just over this little piece, the density is constant so that we can approximate the mass of that little piece is the density at a representative point times the volume. And then we add all of those up. So the meaning of an integral, whether it's a single integral, a double integral, a triple integral, should always be the meaning of whatever the integrand means times whatever the differential means. Okay. Of course, if I had charge density instead of mass density, then that would be charge per unit volume. And if I integrated that, that would be giving me the total charge on an object. I can also then find the center of mass, or the center of gravity, for an object. X bar, Y bar, Z bar would be my center of mass. That would be the point about which all of the mass is evenly distributed. And we can just generalize what we saw when we had functions of 2 variables and we're trying to find the center of mass of a lamina. Okay. X bar is going to be just a ratio. We're going to have the mass m on the bottom. On top, we'll have the moment about the YZ plane. That would be the tendency to rotate about the YZ plane. That's just the triple integral over E of x times our density function. And of course the mass is just the triple integral over E of the density function. And the formulas for Y bar and Z bar are similar. Here's one of my favorite applications of a triple integral. I'm going to say that E is the Earth. Now, to make sense of this application, we just have to make a few minor assumptions. 1, you have become the sole owner of the planet Earth. 2, aliens have landed and want to buy the planet Earth from you. And given that they're going to eat you alive if you don't sell, I would recommend that you do. 3, the aliens value property a little differently than we do. We tend to think of the Earth as a 2-dimensional surface when we're talking about buying land, because we talk about buying land by the acre and stuff. We don't talk about buying the land that's below the surface of the Earth. We just talk about the surface of the Earth. The aliens, they actually care about the entire solid. So I'm going to have a function P of x, y, z, which is the price per unit volume of a piece of land. And this is going to vary because obviously some pieces of land are more valuable than others. So just like with the density functions that we had for mass and charge, I would have to accomplish this function by taking a limit. I would basically chop the earth into little pieces. For each piece, I would find the value of that piece, divide by the volume of that piece, and then take a limit as we shrink to a point, because of course an individual point won't have any volume. Okay. But this would be the limiting function of the price per unit volume as we shrunk to a point. So if I then looked at the triple integral over E of P of x, y, z dV, well, let's see, that would be price per volume multiplied by volume. Ah, this is excellent. If you ever become sole owner of the earth and have to sell to aliens, you can now calculate the price of the earth. Good to know that what we're studying is so practical. Okay, another application is if I wanted to simply integrate over E1 dV. This is just going to give me the volume of E. This is generalizing what we've seen before for single integrals, integral from a to b of 1 dx, double integrals, double integral over d of 1 dA, and now we've got the triple integral over E of 1 dV. I can think of this geometrically. We're going from A to B. We're integrating a constant height function of 1. We're simply getting the area of that rectangle. But the area of the rectangle would be B minus A, that's the length of the base, times 1 would just be B minus A. And so what I'm getting is the length of the interval from A to B. Now the units don't work because technically if I'm integrating here, and this is a geometry problem, this is the area of the rectangle, so it would be square units. But numerically, the number is the same number as the length of that interval. If I have a region D, two-dimensional region, and I attach a constant height of 1 to that region, I can create this solid. The volume, so I'm calculating the volume of that, but that would just be the area of D times a constant height of 1, which is just the area of D. So here, it's like we're attaching a constant hyperheight of 1 to things. So I'm creating this hypervolume, hypersolid, whose hypervolume is the volume of the base E times 1, and that's just going to give me the volume of E. Okay. So in the next video, we'll come back and we'll actually calculate a volume by using a triple integral. See you soon.